we'll do one of those as like a starter problem, and then you'll have some work time. Okay. I'm recording. We're good to go. All right. So today we're going to talk about weak acids and weak bases. This is our next section for acids and bases. And then tomorrow we take notes on titration. When you come back to me on Monday, then I'm going to have the burettes out, which are kind of fancy, almost fancy graduated cylinders in a way, but it has a way to dispense the stuff out very accurately, the solution inside. And you'll get a practice with that where you're just using water just to practice, like, can you, how do you manipulate them? How do you load them? How do you do all of that sort of thing? And then that way you're ready to go for your titration lab on the 19th. Now the 19th, 20th, 21st, 24th, depending on if you're A or B day, that you will need your goggles for, because you're going to be working with acids and bases. They're actually over your head where you have, because these are very long, tall tubes. So you have to have your goggles on for that lab. So you'll need your goggles then, and then you get a 2-day break, and then you're going to need your goggles for the 27th as well. So, okay. All right. So weak acids and weak bases. Remember when we were talking the other day, we talked about the difference between a weak acid and a strong acid, and that's whether they go to completion when they are in water. And what we mean by that, like if we have hydrochloric acid, when it's placed in water, all of the hydrogen for the most part, and all of the chlorine is going to go and break out into these components. But if we have a weak acid, like hydrofluoric acid, okay, when it's placed in water, only some of it's going to go into its ion form. And so we don't actually use an arrow that looks like this. We'll use one of these back and forth arrows, okay? Because some of this is changing into some of this, and some of this is changing into some of this. But the majority of the contents in that sample are going to be on this side of the reaction, okay? So they ionize about 5%. So therefore, they're going to be a weak acid. Remember, there's a difference between strong acids and weak acids, and concentrated acids and dilute acids. Weak acids, like this acid is weak, but it can still kill you, okay? Acetic acid is essentially vinegar, okay? We can get to the point where we have that concentrated enough that it can eat holes through your clothing, okay? Formic acid, this is if you have like certain poisonous ants actually have formic acid that they give off in their bites, and that causes irritation. Carbonic acid is actually dissolved in your blood from the carbon dioxide that's in your blood. You actually have some of that dissolved in your blood. So there's different types of acids here that are weak acids, okay? So the more likely an acid is to donate a hydrogen, the less likely the conjugate base accepts the hydrogen. So a strong acid, most of it will be over here. With a weak acid, it's only partially ionized. All right, so we end up with something called an equilibrium constant, which is a Ka value. All right, remember we had Kw the other day when we were dealing with just water, and we said that was the hydrogen ion concentration times the hydroxide ion concentration. And then we don't put water into the equation, so that's why it was just these two things side by side. All right, and we said that was actually equal to 1 times 10 to the minus 14. And these are an equal amount, so each of these would be 1 times 10 to the negative 7. And that's where they got the pH of 7 for neutral water. So water isn't included in the equilibrium constant because it's a constant value that's much, much higher than the other concentrations. And water is also a pure liquid, so it's not included in that either. So when we look at the Ka values for these weak acids, they tend to come in. Remember, this is the majority, of what's present, okay? So this number down here is going to be much higher than these numbers that are up here. So that means that your Ka value for a weak acid is going to be well below 1. Because that bottom number, no matter what it is, and we're not going to get into those calculations this year, next year in AP Chem, you'll have to do that, or whenever you take it, if you take it. But the Ka value, just understanding the idea that the majority of the stuff's over here versus here, this value is going to be much higher. So that means that your denominator is going to be a higher value than your numerator, which means that your answer is going to come out less than 1. Does that make sense? For your weak acids. Your strong acids tend to have more of this stuff than this, and so their Ka value will be greater than 1. Okay? So again, we're not going to do the calculations this year. I just want you to understand the idea behind what's happening. Okay? And then we'll go into those calculations next time I see you, if I do. The weaker the acid, the smaller the Ka value. And because of that, because the weaker the acid, more and more and more of the stuff is going to be over here, which means this number is going to be higher and higher. So this number will be even lower than 1, like way lower than 1 in really weak acids. Does that make sense? Just thinking about the math of it. I'm not going to make you calculate the math. I'm just having you think about it. All right. We also have what's called polyprotic weak acids. So poly means many, protic means 1. And as we start pulling these hydrogens off, these Ka values get less and less. So citric acid, for example, or do I have an example on the next slide? Maybe I've got one. Oh, here. So this is a weak acid, okay? So we take this guy and we take a hydrogen away and give him here. This is what he's going to look like. See that? Then if we take him and bring him down here and he loses another hydrogen, this is what he looks like. This Ka value for this one is going to be higher than the Ka value down here, because it gets harder and harder to pull another hydrogen away. So there's lots of polyprotic acids. This is actually the first one here. So these are your Ka values. The sulfuric is considered a strong acid for the first hydrogen that comes away. And you can see here 10 to the positive 2, which 10 to the positive 2 is what, 100? Am I doing my math right? Okay. So that would, its Ka value would be 100. But then if you try to take another hydrogen away so that it looks like this, that Ka value is less than 1. That means that the second hydrogen off of here is actually a weak acid. This is strong. This is weak. And you can see here all of these are all the way along the line are way less than 1. So all of these are considered weak acids. And that's why you don't need to worry too much about the carbonic acid in your blood, because it's a weak acid. Most of it stays as this. But if you end up with issues with your blood, sometimes this, with your body, this can get out of whack and you can end up with too much of this in your blood, and then you got problems. All right, so weak bases are the same idea. Okay, ionization is only about 5%, therefore it's a weak base. And the further the equilibrium lies to the products, the stronger the base. So it's the same idea. Okay, you've got your base that's going to be forming here. You've got your HB and your OH. This is your Kb value. Okay, so inverse relationship. Okay, Ka times Kb equals Kw, which equals this. So if you know one of these, you can figure out the other one just by dividing this by that value. Okay, so acetic acid. So you're kind of, what they want you to do here is they want you to show the equation for determining the Ka for a weak for acetic acid. So your acetic acid is HC2H3O2. That's the formula. We're going to put that in water. And what's going to happen is this hydrogen is going to come over and join with this guy. So figure out what your products are going to be based on that. Okay, all right, so you should have gotten your H3O plus, which remember we can write that as H plus, and then C2H3O2 minus. Now, if we're just showing the equation, so this is the equation, if we want to calculate Ka, you're going to have your molarity of your products over the molarity of your reactants, and you don't include water. So we remember molarity we show as these square brackets. Over HC2H3O2 and square brackets. Okay? So, see if you can figure out the equation for NH3 when we put that in water. Okay? See if you can figure out what's going to happen here and show that equation. And then we'll figure this part out in just a second together. Okay, did you get that for your equation? See if you can set up your KB value then for that. Just the equation. You don't have to show me any math. I'm not doing math right now. Do that next year. So we would have the, oh, shoot. Damn it. All right, here we go. So we're going to have the NH4 plus concentration, the OH minus concentration, and that's going to be over the concentration of the NH3. Okay? And then we'll talk about this guy in just a second. Okay? Does that make sense? All right. So remember, that we can calculate. Come on. Are you not going to let me? Oh, because yeah, I told it to keep those, didn't I? Dadgummit. Okay. So remember KB, if we have our KW is going to equal KA times KB, right? So we always know that this value is 1 times 10 to the minus 14. And we know the Ka value for our carbonic acid. We'll look that up in just a second on the previous slide, but we're going to solve Kb here. So if I go back to this slide that has this listed, okay, that's 4.3 times 10 to the negative 7. If I type in 4.3 times 10 to the negative 7, that's going to give me my, if I divide this by that, that's going to give me a Kb value. So you guys should be able to do that in your calculator. I can't. I've got my calculator over here, though. Let me get my fancy calculator. All right. So 1 to the negative 14 and 4.3 negative 7. Okay, there we go. So that Kb value for this guy should end up being 2.33 times 10 to the minus 8. And there's no units on K values. All right, good. Makes sense? All right. So your homework tonight, discard, if this will not keep all of that stuff. Let's see your file, open 18.3, I believe it is, right? 18.3, here we go. All right, so here is what you're going to be working on. So you're going to do the dissociation equation like I just showed you a few minutes ago, okay? Now, how do you know if it's a strong acid, strong base, weak acid, or weak base? Well, a couple of days ago, I gave you a list of these guys, okay? So if it's not on the list, then it's either a weak acid or a weak base. You can also Google it if you really need to. All right. And then the dissociation equation you're going to have written out, which would, for this one, we've already done this one in class. I showed you this one before. This is going to have an arrow going one direction because your strong acids and strong bases, you just have the one direction arrow. That's going to give you H3O plus, which you can just write as H plus if you want to be lazy, and then your Cl minus, right? So then your Ka, you're just showing the equation. You're not going to solve for it, okay? So your Ka expression would then end up being H plus Cl minus over the concentration of HCl. We do not include water in the Ka or Kb expressions. And then you're done. And then you move on to the next problem. Okay, easy enough? All right, so you've got that to work on tonight, and then make sure that you have all of, I want 18, 1, 2, and 3. I'm going to have all of those. The last day I'm going to take those is going to be next time I see you, which is Monday. Okay. Have all of those due that day. And then while you guys are doing your bureau rep practice, I'll be able to get those graded and get your packets back to you. Okay. So tomorrow's titration notes, and you've got a little bit of time to work on this in class. You can probably knock this out in class before you even have to leave. Okay. All right. Kind of gist of everything. All right.
Wait, when you grade them, if we get like a question run, can we do it again? Like you get points back?